In this video, we're going to look at calculating equilibrium constants. Now, we should remember that whenever we're calculating one of these, we're going to find that K, that constant, which is just the ratio of our concentrations at equilibrium when these reactions are going forward and backward at the same pace, is going to be the ratio of our products divided by our reactants. Okay? So whenever we do one of these, it's going to be very straightforward. I've got this first equation, so I'm going to take my K equals my products, which is going to be NO2, and then I'm going to square that because of this 2 right here. I'm going to divide that by the concentration of my reactants. It's just everything's multiplied together. Notice my NO is squared because of the 2 right here, and the O2 just really is to the 1 power. I don't write the 1 power just like I don't write the 1s here. So then that's going to be 1.4 squared divided by 3.5 e negative 8 squared times 2.8 e negative 5. So let's calculate that. That'll give me an equilibrium constant of 5.7 E19. There we go. Let's do another one. This one's going to be the same thing. I'm going to write out my equilibrium constant. What's different here is that now I've got 2 products, and those are both going to go on top. CO, and that CO gets squared. Then O2 gets squared because of this 2. Then divided by, finish my bracket there, divided by CO2, concentration of the CO2, squared because of this 2. If that was a 3, I would have cubed it. Now that's going to be 2e negative 14, not 2 point. And that's going to be squared times 3.5 e negative 3 divided by 3.89. That gives me 3.598, let's go 599. E negative 31, I'm going off the page here. E negative 31. There we go. Next one. And the next one, we have a solid. Now remember, we don't include solids or liquids in our equilibrium expressions. Why is that? Well, if I consider this just in a beaker here. This is the sulfur. It's a little bit of sulfur, which is a nice kind of golden color, sitting right here, reacting with O2 in the air, right? Well, the O2 is going to hit the sulfur here, and it's going to react. The more O2 I have bouncing around in here, the faster this is going to be able to happen, right? If I just keep drawing more of these O2s, every single one of these is an air molecule that is moving independently of the others. But every single one of these would have to hit this pile of sulfur. So it doesn't matter if my sulfur is this big or if it's this big. The reaction isn't going to move to a new equilibrium because it's limited by how many O2s there are. So these O2s, the higher that concentration means, the more O2s that are going to be here hitting this sulfur. But the sulfur is going to have the same concentration regardless of the size, regardless of the mass. It's always going to be just a whole bunch of sulfur right at this borderline right here, right at that edge. That's where that reaction is going to happen. So it's not going to matter if I have more or less of that solid. The same thing happens for the liquid. The liquid is so condensed that it doesn't make a difference how much liquid there is. As long as there's some, the reaction can happen. So when we do those equilibrium expressions, it's going to be K equals, and then my SO2 is my product, divided by only my gases and aqueous products, or molecules. So SO2 divided by O2, so then it's 1.94 divided by 6.4 E negative 9. And that gives us 3E8. All right, and then one more just like that. This one is going to be in an aqueous solution. This would be in a beaker that's containing some silver chloride, some AgCl. And remember, it doesn't matter how much AgCl there is, especially in this example. This example, my solution here is a solution of water. And this water, this H2O, is only going to be able to carry so much sodium and so much chlorine. So we're going to have some silver. Did I say sodium? That's silver. Got some silver. We've got some chlorine. And these are able to dissolve and float around in the solution, but only so many of them. There's only so much that can do it. And it's going to be a concentration. So it doesn't really matter how much silver chloride I put in here. If I added more, well, it's just going to be more sitting on the bottom. This solution would already be saturated. So this solution is going to absorb Ag and Cl until it is saturated with those two ions, and it can't take any more after that. So we don't include that solid. So our equilibrium expression here is just going to include our products, which is just Ag plus, and Cl minus. So we don't even have division in here because we wouldn't divide by anything. We wouldn't divide by that AgCl. There's just nothing there. So we could say this is divided by 1 for the sake of argument. So then that's just going to be 1.24 E negative 14. And since they're the same number, that's just going to be squared. Now, this is going to be the case because if I were to put some silver chloride into that solution, well, it's going to dissolve in a 1-to-1 ratio. And so my concentrations of my two ions are actually going to be the same number. So it's a helpful tip when we work on solubility products. And we end up with a KSP, this is going to be a solubility product, of 1.54 E negative 28. There we go. That's an introduction and a quick overview on how to calculate our equilibrium constants.